Hello students, and welcome to your video lesson on lesson 5.2.4. This starts in your textbooks on page 252. If you want to turn there with me, we're going to start with problem 80. We're going to talk today more about limits, and we're going to talk about how limits connect to the idea of a function being continuous, which we talked about way back in chapter 2 about not picking up our pencil. We're going to get a more formal definition today, which we've been waiting for. And then we'll talk about how limits can relate to horizontal asymptotes in problems 83 and 84. So let's start by looking at problem 80 on page 252. The question starts by asking, for the purpose of defining a limit, does it matter if the function value doesn't actually equal what the limit is? Okay, well, if we think about a two-sided limit, for example, in part A, they're asking about this function here, g of x, where notice they have a hole in the graph. So like we get there, but that point doesn't actually exist. When we think about the two-sided limit as x approaches 3, okay, remember that a two-sided limit means coming from both sides, we need them to agree, right? We need the bug that's walking from this way needs to agree with the bug walking from this way. So in this particular case, I do think that both sides agree. Both bugs think they're going to get to exactly the same y value, the same exact point when x is equal to 3, right? The question is, where do they think they're going to get? This is the limit of g of x. I think they call it g of x. As x approaches 3 from both sides. That limit does exist because both bugs think they're going to get right to this point right here, okay? So the y value they think that they're going to get to is a y value of 2. Okay, so the two-sided limit as x approaches 3 is equal to 2. Now, it's funny because that point, x equals 3, y equals 2, is supposed to be in this graph, but it's not, right? This function g of x is not defined at x equals 3. There's a hole, so it's what we call a point of discontinuity, okay, back from algebra 2, if you remember those. So the function's value at that point doesn't even exist. But that doesn't really matter when we talk about the two-sided limit, right? Because the two-sided limit, remember, is just, do both bugs think they're going to get to the same point? Do both sides from the positive and from the negative agree? In this case, they do, but they're both unfortunately wrong, right? They think they're going to get to the same point. Neither of them is actually going to get there because there is no point for this particular function at x equals 3, all right? So the question is, for the purpose of defining a limit, does it matter if the function value does not equal the limit value? No, it doesn't. That has no bearing on whether or not a limit exists, okay? A one-sided limit or two-sided limit, it doesn't matter. It doesn't matter if it's a hole or if it's an actual point of the graph. Either way, the limit still works the same. Okay, so below g of x, they have a function h of x, which is very similar, except they add a point. They add a point up here, like right there, okay? So this is their function, where the hole in the graph actually does have we do have a y value at x equals 3, right? We do have a y value. It just happens to jump up, and it's defined at y equals 4. Okay, so in this particular case, for h of x, what I could do is I could say h of 3, right? The value of my function h of x at 3 is equal to 4. That's the y value when h equals 3, okay? That's the y value when h equals 3. What they want us to do, though, is they want us to talk about, okay, evaluate the two-sided limit for h of x as x approaches 3 from both sides. So they just want us to change this little function, or this little expression here, to be the limit of h of x as x approaches 3. So again, just think for a second about, you know, if we were to put our bugs on our function, our bug here and have him walk that way, or our bug over here and have him walk that way. Put the antennas on there, give them a little eyeball, okay? Do our bugs think they're going to get to the same spot? Does the limit two-sided limit as x approaches 3 exist for h of x? The answer is yes. They do both think they're going to get to the same spot, okay? And they think they're going to get to the same spot they thought they were going to get to with g of x, right? So remember, it doesn't matter where the function's value is when we talk about the limit, right? It doesn't matter that the function's value is actually now up at 4. It doesn't affect what these bugs think is going to happen as x is approaching 3. So this is still true when we go to h of x, okay? Even though we've put a point at x equals 3 up at 4 in the y, it doesn't change the limit at all, okay? The limit is still what do we think is going to happen as we approach that x value from both sides, okay? So in this case, the limit doesn't equal the value that the function has, right? The limit, we think we're going to get to 2. Both sides think we're going to get to 2, but we're not, okay? We actually get to 4. Our y value is actually 4 when we hit x equals 3, okay? So this is a situation or a case where the two-sided limit exists, but the two-sided limit is not the same as the function's value, okay? So this idea leads us into a formal definition of continuity, okay? So remember back in chapter 2, we talked about what it meant for a function to be continuous. And we just defined it as you could draw the whole function without picking up your pencil, right? Then it would be continuous. The formal official definition of continuity actually involves limits. Okay, so that's why we had to wait till now to talk about it. All right, so what we can do now is we can talk about a function being continuous or a definition of continuity at any specific point in a function, okay? So we can ask, is this function continuous at x equals 5? Or is this function continuous at x equals 0? Or is this function continuous at any specific x value along the function, okay? And there are 3 things that need to be true in order for us to answer yes to that question, okay? So we can call this conditions for continuity. You guys might find that in a box at the bottom of page 252, or maybe it's on the top of 253. I'm not sure how your book is necessarily arranged, but here's our 3 conditions for continuity, okay? Condition number 1, we need, I should say this, conditions for continuity of f of x at x equals some value a. Okay, that's I think how your book does it. So conditions for continuity of a specific function f of x at a specific x value, okay? So what we need is we need f of a to exist. Okay, that's just criteria number 1. If you don't have a point at that x value, then obviously the function is not continuous there, right? So think back to h of x, or excuse me, g of x, when we didn't have this point, right? We just had a random hole in the graph. If the point doesn't exist at that x value, if there is no point at that x value, then obviously our function cannot be continuous, okay? So if it fails that first one, right away, not continuous, okay? So we need f of a to exist. That's number 1. Number 2, we need the two-sided limit to exist, okay? So we need the two-sided limit to exist, which means we need both sides coming from the positive towards that x value, coming from the negative towards that x value. We need those to be the same, okay? No jumps allowed in our piecewise functions, okay? Remember we looked at some of those where one bug thought they were gonna get up here and the other bug thought they were gonna get here. That's not gonna work because the two-sided limit, we would say, does not exist. So we need the two-sided limit to exist. We need the point to exist, okay? And then number 3, we need the y value or the function's value to equal the two-sided limit value, okay? I'll just say the limit value. We need the function value to equal the limit value. So if we think about our h of x example from problem 80, would we say this function is continuous at x equals 3? No. Even though, do we have a y value at x equals 3? Yes, it's right up here. H of 3 is equal to 4. So condition 1's fine. do we have a two-sided limit at x equals 3? Yes, we do. It's right here. The two-sided limit at x equals 3 is 2. Both bugs think they're getting there. Are the function's value and the two-sided limit value the same? No, they're not, right? One is 2, one is 4. So we would say the function's value is not equal to the limit value. Therefore, we fail condition 3, and this function is not continuous at x equals 3. Okay, at that specific x value, the function is not continuous because we failed condition 3. We have to meet all 3 of these in order for the function to be continuous. Okay? So that's our formal definition of continuity. We can check every single point, or for an entire function, we can just try to discuss, the function overall as a whole. But at any specific point, you can check the continuity of a function by checking these 3 conditions. Does the function exist at that point? Does the two-sided limit exist at that point? Do the function value and the limit value agree? Okay? So if we look at number 81, they're asking us to basically practice this with a few random functions where they don't give us graphs, but they actually give us equations. Okay, so if we look at letter A, they ask us to evaluate this function, 1 over x plus 3, and they give us an x value to evaluate. They want to know, is this function, f of x or y equals 1 over x plus 3, continuous at x equals negative 3? Well, let's start checking our conditions, right? Condition 1 says we have to have a function point at that x value. So if I take x equals negative 3 and I plug it in here, what value does my function take when x is equal to negative 3? Well, it's 1 over negative 3 plus 3, which is 0, and that's a big problem for me, right? 1 over 0 is undefined. It's not defined. This would actually be a vertical asymptote. So at a vertical asymptote, could the function possibly be continuous? No. Okay, so A has to be no because we failed condition 1, right? F of A doesn't even exist because 1 over 0 is undefined and does not exist. Now, letter B asks us about the function 2 to the x power, okay? And then they ask us specifically about the x value, x equals 0. So let's start checking our conditions. Okay, can we plug 0 in here and actually get a point? Yeah, 2 to the 0 power is 1, right? So our function's value is 1. The next question is, does our two-sided limit exist at x equals 0? And in order to know that, it's probably easiest just to think about our graph, right? What does 2 to the x look like? Well, here's 1. So 2 to the x would look something like this, right? Where it goes up forever, and then this goes along that asymptote forever, going back to negative infinity. So as I approach x equals 0 from this side, and as I approach it from this side, do I think I'm going to get to the same point? Yes, I do. It's right here. It's right here at y equals 1. So the two-sided limit does exist. Both bugs coming down and coming up think they're going to get to x equals 1, or excuse me, y equals 1 when we get to x equals 0. So condition 1 is fine. Condition 2 is fine. Condition 3, does the limit value equal the function value? Yes, it does, right? It's not a jump or a hole or some random point. It is exactly where I thought it was supposed to be. So this is absolutely a yes. Okay, this is a continuous function. And actually 2 to the x is continuous for all x values. All real number x values. Every single one fits those 3 conditions. Okay, so that's a yes. Letter C gets a little bit trickier because we get now a piecewise function. So I get a 2-piece function. I get 2x plus 3 when x is less than or equal to 2. And then I get x squared plus 2 when x is greater than 2. Okay, and they're actually asking me about x equals 2, that point where I go from one piece to the other. The question is it continuous at that point? Well, the first thing to check is, do I have a value at that point? And because of this guy right here, because of this equal to piece, I should have a point if I can plug x equals 2 into this top part. Can you plug x equals 2 into this top function? Yes, you can. 2 times 2 is 4 plus 3 makes 7. So I certainly do have a function value. So condition 1 is good. Okay, 1 is good. Condition 2, do I have a two-sided limit at this point x equals 2? Well, this is one that we can check actually without the graph, because we can plug x equals 2 into this top piece and into this bottom piece, right? Because from the top side, it's going to be using this function. It's going to be using the x squared plus 2 function. From the bottom side, from the negative, it's going to be using this, right? X less than 2. From the less than side, it's going to be using that. So the question is, are those going to match up? Well, it's just a matter of, do each of these functions have the same value when x equals 2? Now, we know the top piece, right, or the first piece. From the negative side, we think we're going to get to 7. Okay, that's what we think. We think we're going to get to 7. When x equals 2, we just plug it in. The bottom side, where do we think we're going to get if we plug it in? Well, 2 squared is 4. 4 plus 2 is 6. So we think we're going to get to 6 if we come from the top side, and we think we're going to get to 7 if we come from the bottom side. Are we going to have a two-sided limit? No. So this particular piecewise function fails condition 2. Okay, and most often if you have a piecewise function just with like 2 pieces like this, if it's going to fail, it's going to fail condition 2, because you're not going to match up coming from the top side, from the positive side, and from the negative side. Okay, so that's no, because it failed condition 2. And then our last function, letter D, says x squared minus 16 over x minus 4, and they want us to check the continuity at x equals 4. Okay, at x equals 4. So again, we'll check condition 1, plug 4 in. Does it work out? Well, if we plug 4 into this function, on the top we get 16 minus 16, and on the bottom we get 4 minus 4. That's 0 over 0. So that's not going to work. 0 over 0 is undefined. So letter D is again a no, because it failed condition 1. Now this one happens to be a hole in the graph, not a vertical asymptote like we saw in A, but it doesn't matter if it's a hole or an asymptote. It doesn't work out if we have 0 over 0 or undefined. Okay, so that's number 81. Now I'm also asking you to do number 82. Okay, but we're going to skip over number 82, and we're actually going to skip all the way to number 84. Okay, we're going to skip to number 84. We're going to look at that together. Just one quick thing about asymptotes, and we will conclude with number 84. So number 84 asks us about this function, which is a relatively simple looking function, but it's quite complicated in both its graph, its applications, and its limits especially. So this function, sine of x over x, is graphed here. Okay, I've just graphed the positive side. Basically what happens is we see the sine function, but as the x gets bigger, this gets smaller, right? As the x gets bigger, this gets smaller. So we're taking something that's between -1 and 1, and we're dividing it by a bigger and bigger number, so we're getting smaller and smaller and smaller. So what we see is the sine function where the amplitude keeps getting smaller and smaller and smaller and smaller. Eventually it's going to be basically a flat line, a straight line going this way. Okay, what they're asking us to do here in number 84, we're going to skip over part A and not worry about the x-intercepts. But the question is, what is the limit as x approaches infinity? Okay, what is the limit as x approaches infinity for this particular function f of x? Well, as x goes to infinity, as I just mentioned, we have something on the top which is between -1 and 1, right? -1 to 1. And something on the bottom that's getting really, really big because x is going to infinity, right? So remember our sort of rules about 1 over, like something like 1 over something big is something really tiny, or -1 over something big is something really tiny as well. So it should make sense to us that for letter B, the limit as x approaches infinity for this function is going to be 0. Because the top of our fraction isn't changing all that much. It's going -1 to 1, -1 to 1, back and forth like this. But the bottom of the fraction is getting to 100 billion. So anything divided by 100 billion is going to be very, very close to 0. So the limit as x approaches infinity of this function f of x is 0. Okay, and that's part B, which is what we're starting with in number 84. Letter C asks us an interesting question. It says, does this function have a horizontal asymptote? Well, in the past, we've talked about asymptotes as lines that we are not allowed to touch, right? So what I want you to realize is if this has a horizontal asymptote, it would make sense that it would be here, right? It would make sense that it would be x equals 0, or excuse me, y equals 0, our x-axis, right? Because that's sort of what my function is approaching as it gets closer and closer to infinity in the x. But the problem is we've been crossing over this line y equals 0 like infinitely many times, right? We crossed it here, we crossed it here, we crossed it here, we crossed it here, and here, and here, and here, and here. And we're going to continue crossing it back and forth, back and forth, back and forth. So we have to sort of shift our idea of asymptotes now. Okay, we have to shift our idea specifically of horizontal asymptotes. So when we think of a horizontal asymptote, okay, a horizontal asymptote is basically asking, is the function approaching a value as x goes to infinity? Okay, that's really what a horizontal asymptote is about. What value is the function approaching as x goes to infinity? It's basically a limit question. Okay, it's a question of what is the limit as x goes to infinity? So I don't care how many times you've crossed over that horizontal asymptote. Okay, a function has a horizontal asymptote if it approaches a specific value as x goes to infinity, and that value is the horizontal asymptote. So in this case, y equals 0 is absolutely a horizontal asymptote. Okay, now this gets interesting because we can then see different asymptotes as x goes to positive infinity and as x goes to negative infinity. Okay, so you have to ask the question going each direction. What's the function's value approaching as I go to infinity? What's the function's value approaching as I go to negative infinity? Okay, so letter C, does it? Yes. Here's the equation. Okay, we're going to skip over part D as well, but it's just a shift now in our thinking of horizontal asymptotes in relation to limits. Okay, so if you have questions at all about using limits to define if a function is continuous or using limits to define horizontal asymptotes, please reach out to me at some point. Either email, phone call, or Zoom office hours will all work great. Otherwise, that's all I have for you today, and we'll talk to you soon.